So what we have done now, we have done the simulation of the system. um, we have been able to verify that we can excite the DC motor, and we are able to right now do open loop control of our system by varying the input voltage. So proportionally we have been able to increase the speed of the motor as well. But right now in practical applications, once we build the system, we are not happy with this. Normally what will happen is we want the DC motor to achieve a specific speed profile. So now what we have to do right now is we have to build a closed loop system which can help us control the behavior of the system that we want to work with. So now let's see how we can do that. So for that, normally what we focus is a standard approach which we do in every control engineering application. So we have to build a closed loop model like this now. So one thing, we have the plant or the process model already ready made available. We have the DC motor. This is the component right now we want to control. And now this is the setup we have to do. We have to define the expected reference input, and we have to take the actual system output as a feedback, calculate the error, pass it that to the controller with which we want to work with, whether classical control or advanced control. We have all the libraries. So right now we will do classical control here, but I will also show you if you want to do advanced control also, we can do that. We have option available. So then we can do the complete control loop implementation very easily now. Since I have the plant model readily available, we can do that now. So what we'll do here right now, we'll save this Simulink model as of now. So now this should be good enough. Now what we'll do, we will do one more blank model. You can launch one more blank model with the help of this. So using this new button, so we launch one more blank model. And right now what we'll do here, I will minimize it temporarily. I will select this DC motor because this is the motor I want to do control. I want to do the control of DC motor. So I will copy this. I will come back here and I can paste it here. And now this becomes my plant model. So now next what? So this is my actual system which we want to control. So for this I have to implement couple of things. First thing we have to implement, the first requirement we need to have is a reference input. So what is the expected behavior in terms of your speed or the output that you want to control? We have to define that as a reference input. What is the expected behavior of the system? We have to define that as a reference input. Now for this, what I will do now, right now you can see this is a subsystem we had manually created, but in Simulink a subsystem is already available as a ready-made component. You can see that here. You can also manually directly add a subsystem directly as a component. You can see it will be like a simple block. I will add this block. It should look like this. You can see the preview. Whatever input we will give, it will pass the output directly. That is how your subsystem is working right now. You can see the preview also. The input port is directly connected to the output port. And you can see this is the input port, this is the output port. Whatever you will give here, it will come outside directly. That's how right now the subsystem is. But what we will do right now, we will go inside it and we will delete. One thing is this. One more thing we'll delete is right now for this subsystem, there is no need of input port. So we'll delete this also. I need only the output port. So you can see this is the output port. I will keep only this. I will not keep the input port. I don't need the input port. Why? Because I will use the, if you remember, first I had showed you that I can also use a step block as a DC signal. So I'm using a step block. How many step block I will use? I will use 2 number of step blocks here inside this subsystem. And then to add up both the signals, I will use a summation block. Add block or sum block, you remember, both the components are one and the same. So let me use sum block this time to show you it works one and the same. It doesn't matter. It's one and the it's same block. You'll see plus plus is there. If you want to make it plus minus, I can do that. So right now I don't want to do plus minus. I want to do summation only. Whatever component parameters are there, I will update inside this step block. So you can see 2 step blocks are there. This is one and this is the copy of that. So I'm just doing simple summation operation. And whatever the summation output I will get, I will connect that to the output block so that I can take the output outside the subsystem. And right now I will call this output block as reference speed, because we are generating speed as the output and I want to perform speed control of my DC motor, and I can do that. So that is what we are planning to do. Let's see how we can go for doing that. So let us now build the speed profile, expected speed profile. We have to build it. So right now you can see I'm just generating the block and using the copy. That means it will have the default parameters like this, but I will custom. So since we are simulating this for 10 seconds, maybe let's say within 0 to 10 seconds, maybe I will step up the signal around 2 seconds for first step block, from maybe 0 amplitude to maybe a positive amplitude of 5. So that is how I will step up my DC speed, constant speed output, speed profile. And then now we will go to the second step block. So where we will maintain the same, what we can say, so 0 amplitude, we will add 0 amplitude. That means the whatever the final speed output we had got 5, I'm maintaining the same 5 so units of speed as it is by adding 0 till up to 8 seconds, and after that I want to decrease it back to 0. So I will bring it down to -5 after 8 seconds. So we'll click on OK. Now you can see my step block has updated because we have a negative stepping down, or you can say falling edge, so step signal, and we can see the update happening similar to that. Now we can collect the reference speed output here, but what we'll do right now, before we use it in our application, we will internally verify it whether whatever we are expecting we are generating the expected reference input or not. We want to verify it. So we'll do that right now. We'll ignore this block right now. We don't care. We'll just simulate this reference speed block and we'll see the graph output. Yeah, this is good. We can see till 2 seconds it is 0 and we are stepping up to 5 units of speed. We want to maintain the same speed till 8 seconds and then we are bringing it back to 0. So this is the expected behavior of DC motor. I am planning to get it done. Now we have to do that we have to implement a closed loop control system. We'll implement that. We have it, but I'm doing through this. So you can also use pulse generator. Anything is possible. We have multiple options. So again here also I will right click, disable the preview. So this is my system which is generating reference speed. So according to our standard block diagram, this is my reference input block. So now we have the reference input ready. Temporarily I will disconnect the scope block. We will reconnect it completely at the end here. All the input output everything will connect it one single scope block later. But right now we were using it to verify. We have generated the expected speed profile. It's perfect. It's good. So we'll use it as a input in our system. So now what is next? So we have to take feedback. So to take feedback, what we'll do? So we need again a summation block or a add block. So we can use any one of this. Both are one and the same, which is a error calculation block. So I will rename this block as error calculation. This will calculate the error or the difference between the reference input and the actual system output. So your feedback port should be negative. That is the second port in our system. In a control system, we normally go for negative feedback. So we'll go and set up the negative port for negative feedback. So the positive input will be the reference input. So we'll pass that as a positive input, and the negative will be the feedback, which is nothing but the feedback from the output port. So we'll take the connection and we'll give it as a feedback. So this is the output feedback, which will be usually in a control system for stable system implementation. We normally go for negative feedback. So now next, so this will give me the error signal here. So I will just generate a line and I will call this as error signal. You can keep the title like this, up, down, right, left. I think this is good. So now, as I had mentioned here, there are multiple controller mechanisms you can go for. Um, we have a library called control system toolbox, which helps you to implement both classical control as well as advanced control. And you have also family of advanced control library also. Um, right now we'll go for classical control. We'll implement the standard PID controller, which is readily available in Simulink. You can see that. And our DC motor is a continuous system, so I'm going for a continuous. If required, if you're also simulating a discrete system, you can also convert this as a discrete PID controller also. It is a common controller which you can use it as both continuous and discrete based on your requirement. We'll use it. So this is our controller. We'll be using classical controller, which is normally called as PID controller. And I will change the title. This is my controller to my system. So based on the error signal, my controller should generate the necessary control input to the input port of my system so that my output matches the reference input. That is the whole idea. So that's what a controller should be able to do effectively. So we'll connect the output of the controller to the input port of my system. And now we have a closed loop control network readily created. So now we'll focus on the scope connection now. In scope, I want to do two connections. One is I want to measure the actual speed, and also you can say I'm keeping the mouse on the top, on the right side, on the left side corner. And if you do that, you can see a additional port can be added like this. I will generate a additional port and I will connect that to the reference input. I will compare both and we can verify the behavior of the complete system, whether it is my system actual output is able to match up to my reference input definition or not. We can verify it very easily now. So we can see both the output in the same scope block, and we should be able to verify it. So this signal line is generating control signal. So this is my reference speed. The first signal line, which is on the top, this is reference speed, and the second line which we are taking, this is our actual speed. I will talk about that. So as mentioned by one of the audience here, so one of the important factor that we have to do in control engineering is so tuning the PID gain values. So your PID will have proportional, integral as well as derivative gain parameters that is specific to your PID controller. You can see that we have the PID parameters readily available. So by default, you can say this is the default PID gain setting will be every time you implement a fresh PID controller every time. This is how your PID setting will be always. Right now, this is a untuned PID system. Right now we have. So we'll not do nothing as of now. We'll close it. Right now we'll simulate the system and we'll just have a look. So what is happening into my system? And you can see this is the so overall behavior. So right now, since we are observing more than one output, so in my settings, I should be able to activate legends in the scope block so that you can see what is what. So here we can see the yellow signal line is my reference speed expected behavior, and the blue color line is the actual system behavior, actual speed output. And right now we can see our untuned controller is not able to control the system effectively. Why? We know exactly why, because our PID gain parameters are not tuned enough properly. So in your control engineering we have multiple methods where you can derive the PID values yourself. Nichols method is one of the popular method you can go for, but not required. There are many complicated applications where even Nichols method will be not so effective for our applications as you go for complicated systems. So your manual PID derivation method may falter. So in those cases, what we normally do is we will use our optimization library, which is available, Simulink design optimization, which I talked about. We are using that method here, where we have an inbuilt PID gain tuning optimizer readily available, which is called as PID tuner. So we will leverage this and we'll try to derive the PID values automatically without wasting too much time. So how we can do it? We can see we have to expand the window, because at the end we have this button where I can access the PID tuner, launch the PID tuner. So that is what we will do right now. We'll launch the PID tuner, and you can see it will start linearizing your transfer function, your system transfer function, and it will now in the background now it is running our optimization algorithm. It will take few seconds and then it will come up with the final result. You should be able to do that. Yeah, in my case you can see it is highlighting, the window has come up, you can see that here. So it should appear like this. If your system has any instability, you should be able to see some message here that's for certain level of tuning we were able to identify unstable output, so we are ignoring that conditions. It will give you that message, but right now we can see there is no any message. That means so there is no any instability that has been able to find out by my tuner. So we have stable internal parameters, motor parameters, whatever you have taken are stable parameters. And right now we can see in the bottom, so my tuner has been able to optimize PID values at the bottom. You can see that. So we can see the P value, I value, D value has been automatically so calculated, and for those PID values you can see the updated system response. So this solid line is the updated system response. This dashed line was the actual system response before tuning, and you can see this is the graph, and we were able to see this also in our simulation also. And now we can see this is the actual system response now after performing tuning. That is there, that will be normally happening. So now what you can see here, before you can do something, you can analyze your system performance. So we have this option called as show parameters. So you can see if you click, it will take few seconds, because in the background it will take few seconds to calculate the performance parameters. And once it is done, you can see immediately the pop-up window will come up and it will give you comparison before tuning what was the performance parameters, after you have done the tuning what are the performance parameters, So everything will be visible, and as you observed, exactly you can see there is an increase in the peak overshoot of overall 7.12%. 7% of peak overshoot has been introduced to the system now. So now what we can do, you can see, sorry, not maximizing, I will keep minimized only here. So if you are not still happy with these PID values, your tuner is not the end. You can continue doing fine tuning using these tuning tools that are available on the top. Whether you would like to go for frequency domain tuning or whether you would like to go for time domain tuning, it's your choice. You can do the decision. So right now, since we are doing time domain analysis of the response here, I will go for time domain tuning only right now for my case. By default also you can see every time the tuner will be updated for time domain only as of now, because the response will be only time domain. But if you want to go and so do some frequency domain analysis, you can add up those plots and you can do those tuning also if required. But right now we'll continue doing here only. So in time domain you can see there are two set of parameters are available. One is the robustness of the system and one is the system response time. So maybe we'll allow the system response to have time, and let's see what will happen. You can see it is increasing the peak overshoot, so maybe that is not the parameter we are interested to view. We'll bring it back. Maybe we have to increase the robustness, and yes, you can see now the percentage is reducing. Let us see how much maximum peak we can reduce. It is much more reduced. So we can see maximum we can go up to this level if required. We can fine tune the parameter, and you can see every time you are tuning, your PED values are also getting updated according to that tuning, what fine tuning you are doing. And you can see the final results also here, PID values. Now if you are happy with this, so you can close everything and you can click on update block. Now by clicking on this, just wait for a few seconds, you should get this message. Once you get this message, your work is done. Your PID values are now updated to the PID block. Whatever values we have calculated, now it is automatically updated. As you can see in the message, it is updated now. My PID tuner is done. You can see those values will be now updated here. Now we can click OK to update these parameters. Now let us re-simulate the system for the updated system we have, and now you can see we have a much more, not perfect, but better response than what we had earlier. So now you can see we have a much more better system response we have now available. So in most of the applications like this, we also go for control engineering like this, and you can see once you have built the system model that you want to work with, you can easily also take the same model and now you can build the control loop or control strategy, whatever you want to implement for your application. You can immediately go forward and you can do that right away without delaying much of time. So that is also something you can do. So very quickly. So now next what? Right now, so they have informed me. So right now your session has to end by 5. So what I will show you right now, what we have implemented in terms of overall EV application. If you want to do couple of things I want to show. If somebody can help me with Wi-Fi here.
No. ऋषिकेश वीडियो ಹತ್ತೇ ನಿಮಿಷ ಬಂದ ಮೇನ್ ಪವರ್ ಆಫ್ ಆಗುತ್ತೆ ಈಗ होती रही 5 मिनट में ख़त्म होता है 5 ही मिनट पावर सप्लाई ही जाता है हाँ एंड माना बेटा स्ट्रीम
So while that online mode is opening, in the background, what I also want
Covering.
to do is we have updated the overall capability. One of the most common library that we normally work in. So most of the EV applications are two main libraries. One library we have already talked about, which is Similic, which we already know. It's opening the documentation. Let us give it a moment. Yeah, so now we can see we have already now know how to work with Similink environment. Equally important when you are going for multi-domain system application like EV, robotics, most of the practical multi-domain system that you want to work with, fluids, pneumatics, hydraulics, doesn't matter. So electro-pneumatic system, any multi-domain system that you are planning to do, we have a much more better library available where we can build the physical models. And if you are, I think most of the electrical domain people should be familiar with this